In this video, we're going to cover how to solve limits, continuity, and differentiability. Enjoy. Let's make a start. Okay, so this class is going to focus on some more derivative stuff. Specifically, we're going to have a look at limits and continuity. So, limits. What's going on here? Well, the idea of a limit is a bit more useful when you look at what happens to functions as they approach weird spots on a graph. So normally we're talking about asymptotes, but it could also be just undefined spots elsewhere on a graph. The idea behind a limit is to say, okay, we know the value here is undefined or some other weird thing, but what happens if we get close to that value? Just demonstrate the example, we'll look at a quadratic to start with. You wouldn't use it for quadratics, but you would at the very least be able to understand how a limit works from it. The way a limit works is you want to approach from both the left-hand side and the right-hand side of whatever your curve is. So you can imagine going like down the curve. And in this case, we're looking at what happens as x gets closer to 0. The idea is that if you reach the same spot from the left as you do from the right, then the limit is said to exist, and the value of the limit is just whatever y value you got closer to. So in this case, it'd be y equals 0. Same thing as approaching from the right is the same as approaching from the left. Both of those get you to y equals 0. Therefore, y equals 0, well, the limit would be equal to 0. Here's an example where you'd actually use it more effectively, or it would be more useful to use it. If you came from the right-hand side, you're shooting up to positive infinity. But if you came from the left-hand side, you're shooting down to negative infinity. It's diverging. They're going away from each other. And so because they're going away from each other, the limit is said not to exist. There's nothing we can say specifically that we're getting closer and closer to. That's the basics of where you would use limits. You could imagine if you had like a truncus here, for example, at least those would be pointing in the same direction. Although it's worth noting that you would still have an issue there where infinity isn't really a number. And so even if you do have a truncus, which I'll draw up pretty quickly, even if you do have a truncus and you see, okay, they're both going towards infinity, since infinity isn't really a number, you still say the limit doesn't exist because the value, there is no value that you're getting closer to. But okay, that's that. There's a few properties of how the limit could be used. I've never needed to use any of these. These are there on the off chance that you ever come across something that might require them. But for now, we'll just leave that there. So, as far as solving some questions around limits, the first kind of question you'll see is what's known as a discrete limit, which is the limit as x approaches a specific value. Same example as we were doing before, right? It was approaching x equals 0. That's a specific x value. As I said before, you'd pretty much only ever use limits if you're looking at a weird spot on a graph. In this case, we're looking at what happens from a divide by 0 error. So if we had just subbed in x equals 2 directly into this, divide by 0 error, the whole thing's undefined. So we'll make no mistake, the y value at x equals 2 is considered undefined. However, if we do a bit of rearranging, specifically the vast majority of what you will do will be to factorize the numerator. If you factorize the numerator, you'll see that x minus 2 can cancel out as a common factor. And when you do that, what you've essentially done is what's called a removable discontinuity. It was discontinuous at x equals 2, and you've, quote, removed it through factorization. From there, you can sub in your x equals 2 pretty safely, and you would get a limit of 3. Now, it's worth mentioning, this limit of 3 does not mean the y value of this function at x equals 2 would be 3. The y value is still undefined, but the limit would be 3. And what this would actually look like is something like this. I'll start drawing it out. Basically, what you end up with is what's essentially a linear, But at x equals 2, so let's say this is x equals 2, you'd have an open circle there at y equals 3. That's what it ends up looking like. And if you define exactly this function in the CAS, it'll also complain at you. It'll say if you sub in x equals 2, it'll be undefined, even though the CAS doesn't really put white circles on its graphing tool. So defining it as this is a bit more effective, so you can make sure you don't miss out on those issues. Okay, that's discrete limits. The vast majority of what you're doing is factorization of the numerator. The limits to infinity are where your x value is getting closer and closer to infinity. So what happens as x gets closer to infinity? All of these can be solved in the same way, should you wish, although each circumstance has a unique type of solution to it, or a unique result, rather, to save you the effort of working out. We'll go through each of them. We'll go through the process of how you would solve them, just globally, and then we'll look at some of the shortcuts for it. So the first scenario we have is that the degree of your denominator is greater than the degree of your numerator. So under those circumstances, we know that the limit will always approach 0, that being the case. As far as why that's the case, if you want to solve any limit like this, you start by dividing the numerator and denominator by whatever the highest order term is, or highest degree term. So in this case, x squared is the highest degree, and so you divide your top and bottom by x squared. That's the same as multiplying it by x to the power of -2. When you factor all that in, or I guess expand all that in, rather, what you'll find is that when you sub in infinity into all of these spots, because infinity is on a denominator, that's basically just a stand-in for a really, really big denominator. And when fractions get bigger denominators, they get smaller. So an infinitely big denominator would mean that value is effectively 0. So what essentially happened is that every term that wasn't an x squared went to 0. And because the x squared was on the bottom, well, 0 will always be on top, therefore it'll all go to 0 there. So the basic rule is, if degree of denominator is bigger than degree of numerator, don't do any work, just say the limit is 0, because it'll always be 0. If they are equal to each other, then a similar thing is going to happen from before, which was that the only thing that gets to keep its coefficient is whatever the biggest term is, which in this case there's 2 of them. There's 2 x cubes in there, one in top, one in bottom. So both of those, after you do all your simplification, will keep their coefficients, and the answer is just going to be the ratio of those 2 things. So if you have a 4x cubed and a 1x cubed, 4 divided by 1 is 4. So there's a nice and easy shortcut for that. But again, you can do this whole process if you don't want to learn any of the shortcuts, and you'll get there anyway. And lastly, what happens if degree of a numerator is greater than the degree of the denominator? Well, these are always going to approach an infinity. And when it approaches infinity, we say the limit does not exist. Again, x cubed is the biggest. Since there's going to be 2 zeros on your denominator, dividing by 0 is going to cause it to go undefined. The reason why I put an infinity there, a negative infinity specifically, is because that's at least what the TI Inspire CAS will do. Now, sure, you can put that down on your answer sheet. Just make sure you also say the limit does not exist, because, well, as we discussed earlier, going to infinity means does not exist. That's limits for the most part. If anyone wants me to clarify anything before we move on to the next thing, let me know. Otherwise, it'll be continuity. Feel free to interrupt me. So, continuity. Continuity is one of those things that you can pretty much always spot on a graph. Like if you look at this function here, you're basically looking for any white circles on a graph, or just anywhere on a graph that doesn't have y values. Any of the two will mean it's discontinuous at that spot. However, that's typically not what the questions are looking for when they want to say where and why is a function continuous or discontinuous. These are the three criteria you're more or less going to be referring to when it comes to proving or disproving continuity at a point. So the first and most basic thing is that it must be defined at that point. So if we ignored the little green dot here, this white circle would mean that it's just not defined at whatever this x value is. And so first criteria is not being met under that circumstance. Nice and simple. Second point, the limit needs to exist at that spot. We discussed earlier what that was all about. Coming from the right should be the same thing as coming from the left. So if we had, let's say, another example graph that I'll draw up. Let's say we had this and then that, this one being the dark, this one being the open circle. This is discontinuous, not because it's not defined, because it is defined up here, but because they don't join. Right? Limit from the right is getting closer to here, limit from the left is getting closer to here. Now, obviously, you can look at that and say open circle, it's not connected, it's discontinuous. But that will be the criteria that you point towards to say that is discontinuous. Last one's a bit more niche. That's why I've included a MS Paint drawing in there, apparently. And that is that the value of the function at that spot must be the same as the limit at that spot. So here's one where it's just the third point that's violated. It is defined at this spot, right? Because there's a dark circle above at whatever this x value is. It's defined. The limit exists because coming from the left and the right both get you to that white circle. But since the value is up here and the limit is down here, this is discontinuous. So that's the criteria you refer to for this one. So all in all, easy to identify where it's discontinuous, maybe a bit less easy to identify why, or with the wording that they want to use anyway. Differentiability. Pretty much you're doing the exact same thing, but you also want the derivative function to be continuous as well. So the good news about this when it comes to differentiability is that you don't have to go into like this much detail for differentiability. You can rely on your understanding of the functions as they are to pull a lot of weight here. Because a lot of the time when you're the questions that come up around here are pretty much about where is it discontinuous rather than where is it continuous. Because, well, the vast majority of functions are continuous over a large domain. So a lot of the time you're actually looking for the spots where it's not. And so if you're looking at a quadratic, if you're looking at a linear, you know these are naturally continuous. Like over all real numbers, you could plug in anything in here, it'd be fine. And so you can simplify the amount of effort you're putting into it by just looking at the crossover point. In this case, the functions cross over at x equals 0. So you just want to make sure that the y values at those spots are the same, which means sub in x equals 0 into both, which is what we're doing here and here. And then you just want to see, are those y values the same thing? And in this case, they are. So we can say f is a fully continuous function over its domain. But because we're trying to prove differentiability, we also want to do the exact same thing for the derivative function. So when it comes to doing derivative of a piecewise function, you just do it line by line. So derivative of this is that, derivative of this is that. And then from there again, test that crossover point. X equals 0 for both, derivative and derivative are both derivative equals 3. As far as what to look for differentiability, if the function is fully smooth, so that join up is super smooth. If it's smooth, it's fully differentiable. If it's jagged, so if we have like a graph like this, if it's got a sharp edge on it, it is not differentiable at that spot. And it's worth clarifying that at that spot specifically. It is differentiable elsewhere, that's all fine, but just not there. Yeah, and as far as what that would look like, it may be the case that your function is continuous, because this one is a continuous function. Like, it joins up there. That's no issue. It's just that when you then go and do the derivative, and you check the gradients at those spots, very different, 3 and -5. And so what's essentially happening there is, because you've got discontinuous gradient function, in fact, you can even have a look at what that might look like if I quickly sketch out that graph. So for less than 0, you've got -5, which would be this, -5. And then for greater than or equal to 0, you've got -2x plus 3. So you'd start at the 3 and shoot down. Yeah, shoot down because it's negative. That's a weird one. And so, because you can clearly see the discontinuity there, there's a massive jump. This is not a differentiable function at x equals 0. That's pretty much it. That's all the content for today. Otherwise, if you don't have any questions, we can get into textbook questions. Okay. Yeah, here's some more examples of like piecewise. So you can see defined at x equals 1 because there's a point hanging here, but like a limit, right? So limit coming from left is at y equals 1, limit at right, y equals 6, actual value, y equals 5. So not continuous. Continuity. Yeah, just all sorts of graphs like that. Yeah, okay. So we'll get into some questions. I'll pick out the ones that actually should be solved. Because like if you look at A through E, there's no real point to use a limit here. It's just subbing in the function because there's no divide by 0 in any of these cases. There's no actual effort to put into it. But however, there is a bit of effort if you're going to put it into part F, for example. So we'll have a look at that. I'll start writing it out. In the meanwhile, have a think about what you might do to solve it. Lim x approaches 0 of x plus 2 all squared minus 4 all over x. And of course, it's not going to focus. There we go. Alrighty. What might we do? That ring light makes it so much worse. So we can't just sub in an x value immediately, right? If you do that, you're going to get a divide by 0 error. So our goal is to try and get rid of that divide by 0. What might we do to get rid of it?
Chris, would you first want to factor in the -4?
Factor in the -4. Not
Like make it x plus 4 times just x?
x plus 4 times x plus 4 times x.
Because like when you bring it back into the brackets,
Bring it back in. Oh, like as in.
you square root it and then you bring it back in.
That's for multiplication and division, not for subtraction addition. What you're talking about there. But fair enough. It'd be more so if it was like multiplied by 4. You could bring it into the brackets by square rooting it on the. By square rooting it on the way in. So not quite for addition and subtraction. Your better bet here is to expand the quadratic. So you'd have your x squared plus 4 and then plus 2x by expanding it out. And then that's actually the way you're going to cancel out that 4. So plus 4 minus 4, and then, well, everything is now divisible by x here. So x squared is going to become x, 2x is going to become 2. Reminder that there was a limit here. And so at this point, we can pretty safely sub in the x equals 0 because now there's no divide by 0 error. So the limit becomes 2. But no, fair point even bringing that up. A lot of people won't usually think about being able to put things in and out of squares or roots. So I like that you're at least thinking about that. Quick question though. What is the value of the function at x equals 0? Be a test of theory.
0.
Why 0?
When we sub it in, you just get 0/0.
Yeah. So is that 0 or is that something else?
I actually think that might be undefined.
Undefined. Yeah, better. So any divide by 0 error, the actual value will be considered undefined, but in this case the limit was 2. This would end up looking like a linear. It'll look like the x plus 2. So if you were to sketch what this whole thing looks like on a CAS, it would look like this. So cuts through y equals 2. This would be a negative 2. But then at x equals 0, you'll have an open circle on that crossover. That's what that ends up looking like. Okay, that's that one. What else is good to do? Yeah, sure, we'll do G.
Wait, Chris, I just had a question about this quadratic.
Yeah.
When you expanded it, why is it like a 2x on the outside? Wouldn't it be like a 4x? X squared plus 4x plus 4?
Oh shit, you're right. Yeah, I'm just dumb. That's a 4x.
And then it'd be x times x plus 4?
X times x plus
When you
x
like,
squared plus 4x, and then that becomes x plus 4.
yeah.
Yeah, that's my bad. I should have put a 4x there. Yeah, no, good point. So that'd be 4. That'd be negative 4. Yeah, thanks for catching that. Yeah, okay, that's that one. And so going to have limit as t approaches 1, and we're doing that for t squared minus 1 over t minus, yeah, that's right, t minus 1. Again, same issue, sub in t equals 1, you got to divide by 0. What are we going to do?
Do you want to factorize t squared minus 1
Yeah,
to t plus 1 times t minus 1 and then cancel out the common terms?
that's exactly right. T plus 1, t minus 1. So that can usually be a bit harder for people to see. The way that works is because there was no t in here, you know that whatever factorization you do has to end up cancelling out the t. So it's always going to be plus minus whatever the number is. T minus 1, those cancel, t plus 1, and then you sub in the t equals 1 to get limit equals 2. That's all. Nice. Is there any others? I mean, look, at this point we're just testing our factorization knowledge. If anyone wants to do any more of those to practice factorizing quadratics, feel free to let me know. Otherwise, we might be better off moving on to question 2 if you guys are all happy with your factorizations. In the meantime, I will grab a summary of, yeah, these are good to have. So I'll put this in the chat in preparation for the next question. If you want to do more, as I said, let me know. Otherwise, question 2. So given the actual x value here, not so challenging. What if we're doing like 2a, what x values would be discontinuous? Or at least what spots on the graph would be discontinuous?
When x is 3 and 4?
Yeah, x is 3 and x is 4. Both of those would be discontinuous. Reason why, of course, being the white circles, and well, if you wanted to also think about it, the gap here as well. It's also an issue. Now, this is the tough part, or maybe tougher part. That's why I gave you a screenshot to refer to. Give reasons. So we'll do this one by one. x equals 3. What's wrong with that? Which criteria isn't met? There are multiple answers to this one.
Chris,
Yeah.
is it because the open circle, like, it means it's including 3? So wouldn't that mean like the limit doesn't exist at that point?
Well, the open circle means it's non-inclusive, so it's the opposite.
Oh, my bad.
That's fine. As far as the limit not existing, a limit exists if you get to the same spot on the graph from the left as you do from the right. So from the left is getting us to this white circle. From the right is also getting us to this white circle. That's a bit of a weird one because you think it might terminate here. It does actually mean you look at this part on the graph as well because you're looking here. And so the limit actually does exist here because you're coming from either left and right to get to this spot. Whereas if you're looking at this one over here, you can't really justify that anymore because there's no way to get it anywhere closer here. But okay, limit does exist here. The issue is that there's no dark circle anywhere else here for it to be defined. Therefore, it's that first criteria that isn't being met. And then basically, yeah, every single time the first criteria isn't met, the third criteria also isn't met. Because if there is no value, then there's no way the value could be the same as the limit. But when you're giving your actual answer, the only one that will, yeah, I guess if you wanted to be super safe with it, you might give both answers. But the only one they're actually really caring about, at least as far as I'm aware, would be that first answer. It's just flat out not defined. But okay, that's the x equals 3 one. Kind of gave away the x equals 4 one. What's the issue there? X equals 7 isn't... Oh, yeah. So you're looking at part B then. Yeah, x equals 7 isn't defined, yeah. Why? What's the... Oh, actually, sorry, no. X equals 7 at this spot isn't defined, but because there's a dark circle on the top here, it is technically defined, just not on this curve, but on this part of the curve. So white circle doesn't necessarily mean always undefined everywhere. It's the same thing over here, right? White circle, but nothing above it or below it, definitely undefined. White circle with dark circle above it, it is defined, just up here at x equals 4. Is it clear enough, the nuance there? But like, good job, like having a go at it. Like, I appreciate the engagement. It's good to, I think they call it failing forward, so to speak. You're learning, which is good. But okay, so for x equals 7, if it's not that, what is the issue with x equals 7? I was talking about it a bit earlier from here, over in A. It's just, so the x equals 4 one in part A and the x equals 7 one in part B are discontinuous for the same reason. I'll say that as a hint. Maybe we'll even go down the list. So, first one, is it defined at a spot? That's what we were talking about earlier. even though it's not defined here, or yeah, that's right, Crush. It's because of the limit. I'll just finish the sentence though. That being that even though it's not defined at the white circles, because there's a dark circle immediately above it, that does mean a tick for criteria 1. However, it's criteria 2, as you've said. The limit does not exist. Reason why? Coming from the left gets us here. Coming from the right gets us here. Those are two very different things. Coming from the left gets us here. Right gets us here. That wasn't the case for this one, because even though there's a gap like from the right hand side, because there's still some runway to work with, you can say that from the right gets you here and from the left gets you here. That's why a limit wasn't an issue for this one, but it is for the other two. And just to be super clear, if any of these two are not met, then the third by definition is also not met, because the third is based on the first two. So your only other possible answers will be 1 and 3, 2 and 3, 3, or even all 3, I guess. If you had like a white circle here as well, that would be all 3 of them. Yeah, that would be all 3 of them. Haven't seen that though. But okay, that's those ones. Question 3, question 4 are the exact same as part 2, except now you've got to actually sketch those piecewises. So maybe we'll do a bit of revision for sketching piecewise. If we were to do, we'll keep it simple with the part A, just linear. While I write out the question, who can tell me how to start sketching a piecewise? Or at least just what we do, broadly speaking, for sketching piecewise. Yeah, go line by line is correct. Certainly. So, piecewise, the way it works is each of these are their own separate function, but you're basically sketching them both on the same axis. So hair on there, is that just the ring light? Oh, this is the ring light. Yeah, so basically the way this one works is you'll be sketching 3x, the graph of y equals 3x, for all x's greater than or equal to 0. So 3x is just a positive linear, so it would shoot up something like that, starting at 0, because it was an inclusive, the including 0, you'd do dark circle, and then minus 2x plus 2, well, that's going to have a y-intercept of 2, and because it's a negative, it would point downwards into that. And so it would end up looking like that. I don't know why I made it thicker. It would end up looking something like that. And this would be an open circle because, well, non-inclusive inequality. All right, now that we have our function, what's wrong with it? Where is it discontinuous and why?
The limit isn't like defined at x equal to 0.
That's it. Yeah, the limit's the issue. The value is fine, right? That's right there at the origin. The limit kills it at the y equals 2 and the y equals 0 on this side. 2 does not equal 0, therefore the limit's the issue. Nice. Okay, that's the same as part B, part C. You just got to know how to sketch quadratics and linear. So, whatever. And because some of them are 3-stage piecewises, you'll have more spots to look at, presumably, when it comes to continuity. Okay, and then lastly would be differentiability. So the way the book's written this is that a function is differentiable at x equals a if the differentiation by first principles works, more or less. Like, can you actually do it? Because there's limits involved, you can sort of just chunk up and use the criteria of continuity, because that whole thing is pretty much defined based around limits as well. And so you can chunk up a level and just say derivative function and original function, continuous. As I said before, anytime you can identify a sharp edge, so this would be considered a sharp edge, it would be non-differentiable at that spot because, well, this is going to have a gradient of 0, this is going to have a gradient of, well, I guess 2, this one, 2. And so because those are two different things, the gradient graph would look like that. You can clearly see the discontinuity. It's worth mentioning, when you go to derivative, because it was discontinuous at x equals 0, you actually don't give the spot to any of them because you can't actually say that derivative is defined anywhere here. So basically, whenever you have sharp edges, when you're doing your derivative graph, even though this one was inclusive 0, when you do your actual derivative, both of them should be non-inclusive there. Bit of a weird thing. You might not expect that. I believe it's purely just because of like this criteria here. Coming from left does not get you the same gradient as coming from right, and because of that, we can't say gradient is defined there at all. Okay, that's that. Yeah, okay. What are we doing here? Sketch f dash. Yeah, we could do at least one of those maybe. Sketching f dash. Is that all it's actually asking? F dash should be 0, gradient 0, negative. Yeah, okay, fair enough. So all we're going to do is do a sketch of f dash, and if applicable, we will have a look and see if there's any continuity errors. Okay, so I'll just make a copy of f. This will be a bit of revision from, I think we looked at how to sketch derivative graphs before. If not, we'll look at it now. Okay, so it's something like that. And then, does anyone know how we start writing or drawing the derivative graph? So when I say derivative graph, I mean if you were to do the derivative of this, how you might draw that, even if you don't know the rule.
Don't like the turning points and like the point of inflections become like the x-intercepts of the derivative graph?
That's it. That's exactly why. That's exactly right. Do you know why that's the case though?
Um, because like derivative is like, the gradient of like the original function, right? So when you sub in like, the x value, like, for the turning point in like the original graph, you get like 0. Like if you sub it in the derivative graph.
That's it. Yeah.
Yeah.
And so those zeros, because derivative gradient is on the y-axis of our derivative graph, and so yeah, any turning point, because it has gradient 0, will therefore mean essentially a x-intercept at these spots. That's supposed to be the origin, so I'll do that. And then this one down here, what we've essentially done is segment our graph by doing that. We figured out all the key features of turning points. What do we do once we have that?
Join the points, I guess.
Join the points, yeah. We will be joining these points. I guess the question becomes how, because there's a couple of ways you could do that. You could do, you could do that. You could do that. You could just draw a straight line. You could do all sorts of stuff.
I mean, you would have to draw like a cubic graph, but it would be positive, I think.
Overall positive cubic.
Positive or negative?
this will be a well, actually, this is a quartic, yeah, based on the number of turning
Yeah.
points. So for everyone else, by the way, if you're looking at a graph that has a bunch of turning points in it, a nice rule of thumb is just +1 to the number of turning points, and then that will be your polynomial. So instead of having, well, because it has 3 turning points, you've got a quartic. So basic quartic, it's not going to be, but let's say it was negative x power 4. Negative because it's pointing down, right? If we were to do derivative of this, do you know what it becomes?
Negative 4x to the power of 3.
Yeah. So that implies a negative cubic for this one here. And so that's, perfectly one way of doing it, right? Which is just, this is a negative quartic, so I should get a negative cubic. And negative cubics start top left and bottom right. And so I can just use my understanding of sketching cubics to do that, because I go from quartic down to cubic. Perfectly fine. Not necessarily the only way you could do it. One of the ways I'm recommending is to, now that you've separated the graph up into stationary points, is you can look left and right of each of those stationary points and just say, what is the net gradient? That's what I was drawing these lines for. Like, net gradient up here is positive, and so on a gradient graph, that should imply positive y values. Then net negative on this section here, so it's going to have negative y values. Net positive, positive y values. Net negative, negative y values. So if you prefer, like if you've got a crazier graph, like if it's not clearly a quartic or clearly a polynomial, then that becomes a bit more effective, just by dividing it up into stationary points. Although, come to think of it, I don't really think there's many graphs that aren't polynomials that have stationary points. You've got circular functions, but I mean, that's about it really. So, I mean, there are other weirder graphs. Point being, this is a more general purpose way versus just a polynomials exclusive. Is there anything I should clarify there? Let me know. Oh, actually, there is. Limits and continuity. So, is there any stage around here which would be considered discontinuous? And if so, why or why not? Might be a bit of a trick question. Quartics, are they naturally continuous? Is there anything really wrong with that usually? And like when I say that, it's usually, is there anything that would cause the math to go weird, like divide by zeros or negative square roots, that sort of thing? Is there anything inherently wrong with continuity when it comes to quartics?
No.
Yeah, correct. Nothing really wrong. And so it's pretty good guess that from there you could now look and say, well, derivative is probably not going to have any issues either. But you probably also want to look at the derivative as well. We've seen cases where derivative could also be discontinuous. But, we've gone from quartic down to cubic. Does cubic have anything wrong with it as far as divide by zeros? The answer is also no. And so, yeah, this one's fully continuous. Nothing wrong with it. Don't know how that zoomed out, but okay. Cool. So that's a bit of revision for sketching derivative graphs. We won't do that for all of them, but we will talk about, I'll zoom out a touch on this will do for zoom. Parts B, C, D, E, F on the book. We're just going to talk about where there would be discontinuities as far as differentiability is concerned. So where would there be non-differentiable spots on any of these graphs? Yeah, we'll just do them in order. So who can spot the first issue with differentiability in any of these graphs?
I think part C has a like issue where the like at x equals 0
Mhm.
where the two lines meet up.
Yeah. What's wrong with it?
Like
Yeah, you're correct, but what's wrong with it?
I I remember like you saying like if the function meets up at like as like a jagged point,
Mhm.
it's not continuous.
Yeah, yeah, super correct. Um, yeah, I guess it is a bit of a loaded question because you wouldn't necessarily say that on your sheet of paper. What you would say is that gradient left is different to gradient of right, and therefore discontinuous. Like gradient immediately left and immediately right would be different. Whereas when you look at like part B, it is a smooth joining there, so derivative function will also be smooth. This would be like as if you had done two like piecewise linear. This has a gradient of, well, negative something, because there's no y value there. This has a gradient of positive something, sharp, discontinuous. With that in mind, you can probably spot the others fairly quickly. I won't ask for justifications anymore. Um, but whereabouts would the issues be? And this part F graph is horrendous where they've put them. But try your best, I guess, to explain it. Or at least state where they are. In fact, don't even worry about part F. It is just jagged edges. Part E might be a little bit harder to tell. Where's it discontinuous there? Well, sorry, not discontinuous, non-differentiable.
Like before both the graphs meet at the y-axis.
Yeah. So might be a bit harder to justify that as a sharp edge. It is a sharp edge, but since it's a non-typical looking thing, might be a bit hard to identify that. But yeah, it is the same thing. Sharp edges. Now, I don't know if this is intentional or not, but it looks like they had more space to draw the graph and just didn't. If it was intentional to drop the graph here and here, these would also be spots of being non-differentiable. Could anyone tell me why? Like if these were, we'll say they're closed circles. Think about the criteria from earlier when it came to what I said was required for a function to be differentiable. It had close ties to continuity. What might be wrong? Well, maybe nothing wrong, but let's what are the criteria? Well, what is the criteria for differentiability? We'll start there. There's a screenshot with the answer in it. Oh, wait, no, there isn't. It's just continuous. Yeah, okay. So for differentiability, I mentioned earlier that you need both the original function and the derivative function to be continuous. So you're looking through these three criteria for both functions. So when I'm saying that there's dark circles here and here, dark circles already tell you original function's fine, right? You've met the criteria you need to. Derivative, however, you run into issues because you can't do a limit on this because you can't go from left and from right when you're doing the derivative side of things because there's nothing to compare it to. And so for that reason, you end up having a discontinuity on the derivative function. It's a bit niche, I'll say that much, but just in case it comes up, that's something to watch out for. If there were, like, even though it's got dark circles there, you think, yep, cool, that's continuous. Not necessarily the case for derivative because, well, it's truncated. But okay, that's that. Part F, that was pretty straightforward, just all jagged edges. There's F, sketch F dash, except this time they're giving you the piecewise instead of a graph to work with. That's just piecewises. Yeah, those are that. And then for each of the following, where is the derivative defined and sketch it. Okay. These all have something in common with them that causes them to have a spot where the derivative is not defined. I guess the first thing I'll ask is maybe, if not the answer outright, what's the commonality between all of these?
They have a fractional exponent.
Yeah, fractional exponent, correct. There's actually something even more specific about the fractional exponent that would cause it to have an issue regarding differentiability. Reminder that differentiability is all about like your gradient values. What is it about?
They're also like none of them are like even.
Yeah.
Like there's no like x to the 2 or x to the 4 or
So-
second square root or fourth square root.
Yeah, correct. So what about that makes it weird as far as spots that could be non-differentiable?
There's curves basically.
Yeah.
There's terms in the function.
I guess maybe one thing we'll do is we'll look at a reference function. Do you know what the shape of x to the power of a third is? So just basic old f of x equals x to the power 1 over 3.
It's like a cubic, but like you like put it horizontally.
Yeah, correct. So it does something like that. This should be flatter. I'm just bad at drawing. So imagine this pointing basically vertically at that spot. What's weird about this as far as gradients are concerned, or derivative is concerned?
X equals 0, isn't it like more than like maybe 1 point that's like that would intersect, like then the limit wouldn't be defined?
More than 1 point that wouldn't. Could you try explain that again, sorry?
Like you see how like a lot of it's like on the y-axis. I'm not sure if it's just
Yeah.
because of the look of it or like does that
Oh,
mean
yeah, okay. I was just trying to emphasize that it's supposed to be perfectly vertical at that spot. So, like, yeah, can I do it better? Like that kind of thing. It's instantaneously vertical at, yeah, it's even worse, actually. If I zoom in enough, maybe it'll look better. Yeah, I didn't even get the axis right, goddamn. There. It's instantaneously vertical there. What do we know about vertical lines as far as their gradient's concerned?
The gradient is undefined.
Undefined, yeah. That's what I was trying to emphasize with the graph. And clearly failed. Because when you have, yeah, is that right? Every time you do the inverse of a stationary point, the gradient becomes undefined, because instead of being a 0, it's now a 1 over 0. Yeah, that might be true. Anytime you do inverse of stationary point, it becomes undefined there. It's kind of what you do with tan. Anyway, I wouldn't take much. I wouldn't look too deep into that specifically. That's just me musing. But point being, all these graphs have that kind of behavior where they have an instantaneously vertical spot on their graph. So that was the power of a third one. It did have a translation of 1 to the right on the book, but whatever. It just means it's discontinuous, or sorry, non-differentiable at x equals 1. The power of a fifth is the exact same thing, but just even more drastically. In fact, at this point, it'll be better on the CAS. So here's the x to the 1 over 3 that we were talking about earlier. It is instantaneously vertical. Well, okay, shouldn't zoom in that far then. Vertical there. Any higher odd denominators is just going to cause that to be more pronounced. So if I go 5, you'll see it's a bit more pronounced. Every odd number past that will be more pronounced. And then when we compare that to the 2 over 3s and the 2 over 5s, well, before I do this, what do you think might happen to the overall shape when you put a 2 in that numerator instead of a 1? And if not that answer, what does it mean? What normally happens when you have power 2?
It's squares.
Yeah, squares. So if you were to square what you're looking at, which is essentially what that means, put a power of 2 in the numerator, what does it look like when you square this graph?
Will the y values in like 1 over 5 like dilate by 2?
Dilate by 2? Dilate's the wrong word for that, but I get what you mean, which is because you're squaring it, it'll like make the y values bigger because you're squaring them, at least as long as they're greater than 1. Yeah, it's going to have a dilation-like effect, at least for the right-hand side. It will happen on the left-hand side as well, but there is something more significant that happens on that left. What's also fun about squaring a number? What else do you find in your regular algebra when you square things?
If you square negative numbers, it becomes positive. Is that?
Yeah, exactly right.
Yeah.
So that left-hand side is now going from bottom to top, and you saw, maybe you caught it, maybe you didn't, but also the steepness of the curve increased a little bit because, as you said, squaring is kind of a dilation factor. So instead of being that steep, it's a little bit less steep on the previous one. Yeah, exactly right. You've actually seen this before on a truncus, where squaring the bottom flipped the bottom of the hyperbola to be on the top part now. And so you can imagine that as power gets bigger and bigger on the numerator, well, even anyway, more bigger and bigger even numbers will just cause it to shift higher and higher up that y-axis. Yeah, I mean, I think we've explored about as much as that could be explored. Odd denominators mean it's going to be cubic, inverse cubic like, and then even powers will flip the negatives to positives. Cool. All right, I'll hang out for a bit. Otherwise, if there's no questions, feel free to enjoy the remaining minute that I've given you back. All right, take care.